So in this video we're going to look at Rolle's theorem, which is a special case of a more general theorem called the mean value theorem. Now, in this video we're going to prove Rolle's theorem, and the subsequent video in the playlist on real analysis is going to be on the mean value theorem, and we'll see how this more general mean value theorem follows really easily from Rolle's theorem. So let's firstly state the theorem. So we're going to have a function that's going to be defined on a closed interval that we'll call the interval AB, and it's going to be a real valued function. And for Rolle's theorem to apply, the function is going to need to be continuous everywhere on the closed interval AB, and it's going to need to be differentiable everywhere on the open interval AB, so everywhere inside the interval except for the boundary points A and B. Now if it is differentiable at those boundary points, then Rolle's theorem will still be applicable, but this is the weakest condition you need to be able to apply Rolle's theorem. And then the final condition is that the value of the function at the two endpoints of the interval, f of A and f of B, are going to equal one another. Rolle's theorem is then, if you have a function that obeys all of these, you can conclude that there is a point somewhere in between A and B, so in the open interval AB, such that at that point the derivative of the function is equal to 0, f prime of c is equal to 0. So this theorem is very intuitive, and in order to explain it to you intuitively, I've drawn this picture here. So here is our domain, this interval AB, and then we've graphically plotted our function f defined on our interval AB as this curve here. And you'll note that I've drawn the value of the function at A and the value of the function at B equaling one another. That this value here, f of A, is equal to f of B. This red line is showing that level. Now, because we know the function is continuous everywhere on the interval AB, that intuitively means that we can draw this graph continuously. We can put our pen down at this point and draw this line, and we can get all the way to the other point, perfectly plotting our function without ever having to take our pen off the piece of paper. There are no breaks in it. We can plot it nice and continuously. The intuitive meaning of it being differentiable everywhere inside the interval on the open interval AB is that for all of these points inside the interval, the curve is going to have a tangent line. So there aren't going to be any sharp corners. There's not going to be something like this, for instance, over here. This is a point where the derivative is not going to exist. This corner doesn't have a tangent line. And if you think about having all of the secant lines converging in towards your point, from this side you can see that they're converging on this sort of thing, whereas from this side they're converging on this sort of thing. So that's why the derivative isn't going to exist, because the right hand limit and the left hand limit of the rise over rung quotient are going to approach separate things. So what Rolle's theorem is intuitively saying on the picture is that for such a function there must exist some point inside this interval AB, our point C here, where if you look at that point on the curve, its tangent line has gradient 0, i.e. the derivative at that point is equal to 0. And the intuitive reason that that's going to be true is either the function can be a constant function, so it can just be a straight line connecting these 2 points, a horizontal straight line. And in that case, of course, the gradient of the tangent lines is always going to equal 0, so every single point within the interval would satisfy being your C, because all of them would have derivative equal to 0. Or, if it's not a constant function, then at some point it either has to go up or it has to go down. And if it goes up, at some point it's going to have to turn around and come down. And at that point where it turns around, its maximum, it's going to have gradient 0, because remember, this thing isn't allowed. You're not allowed to have a sharp corner at your maximum there, because at that point then it wouldn't be differentiable and wouldn't fulfill this criteria. Equally, if you go down, at some point you're going to have to turn to come back up, and at that point, that turning point, you're then going to have a gradient 0 again. Again, you're not allowed to have the equivalent sharp corner for a turning point in this case where we've gone down either, because it would break this criterion. So that's the intuitive explanation as to why this is going to be true. Now what we'll do is prove it with full analytical abstraction and rigor. So the first case is actually to consider this special case, which is the constant function. So imagine now that our function is this straight line, this horizontal straight line connecting this point to this point. So f of x is going to equal f of a, which is equal to f of b for all x on the interval ab. Now in this case, the derivative of the function is actually going to equal 0 for all points in that open interval from ab, and that's because if you consider the way we would find the derivative at a point x, we'd consider taking the limit as h approaches 0 of f of x plus h minus f of x divided by h. But for all x, f of x is just this constant, and f of x plus h is going to just equal this constant as well, because that's all the function ever equals. So the numerator is going to become very boring. It's going to be f of a minus f of a, which is just 0, then divided by this change that we've made in x, h. Now, of course, we're not considering h being equal to 0. We're taking the limit as h approaches 0, but that has nothing to do with what the function actually equals when h is equal to 0. It's not defined when h is equal to 0. And for all other cases where h doesn't equal 0, 0 divided by something non-zero is still just 0. So we've just got a constant function that is 0, 0, 0 everywhere. So the limit as h approaches 0 of this constant function 0 is just going to equal that constant, which is 0. So therefore, the derivative is 0 everywhere, which fits with your intuition that, this horizontal straight line every single place is going to have tangent line of gradient 0. So Rolle's theorem is clearly true in this first special case. Now let's consider the other possibilities for this function. So I've split it into two further cases that we need to consider. So if the function is not just a constant function, a horizontal straight line, then one of these two must be true. Either there must exist at least one point in our domain, so on the open interval ab, such that when you look at what the function is mapping that point onto, it is bigger than what the endpoints are being mapped onto. So this looks complicated, but all it is saying is that one possibility is that you must go up at some point. If you're not a constant function, then at least one point must be above it. The other possibility is that there must be at least one point that is below the values at the ends. So there must exist an x is an element of the open interval ab such that f of x is less than the value at these endpoints, i.e. the function must go down. Now, of course, you could have a function that has both of these. You could have something that goes up and then comes down and then goes back up. That would have points which are being mapped onto something below this red line and points that are being mapped onto above it. That's fine. We just need one of these to be true. In that case, both of them are true. That's brilliant. But we just need one of them to be true. And for every function that is not this constant function, at least one of these must be true. So every function that satisfies this will be in one of these three categories. This category is very small. There's only one function in that category. But these two categories are much bigger. Now, some functions might be in both categories. That doesn't matter. This function that we've drawn here, it will only be in this category because there are no points in the domain that are being mapped onto a value lower than f of a and f of b. So if we prove that Rolle's theorem is going to hold true for functions in these two categories, we will then have proven it for all functions that satisfy these criteria. So we'll prove this second case here in detail now. The proof for the third case follows the exact same strategy as this second case. So we won't go into detail for the third case, we'll just outline it after we've done the second case. So for these functions that satisfy this second case, we know that at least somewhere on the domain, the interval ab, the function must go up. It must get a value that is bigger than this. So our original picture up here was a function that would have satisfied this second case. I've drawn another picture that's very similar to that, showing how this function goes up above this value f of a, f of b. So this would also go under this second case. What we're now going to do is apply the extreme value theorem. So the extreme value theorem is about functions that are continuous everywhere on a closed interval ab. It tells us that such functions, one, they must be bounded, so both bounded above and bounded below, and two, they must obtain their minimum and maximum. So we know from our initial criteria that we had for even being able to apply Rolle's theorem that our function is continuous on the closed interval AB, so we can apply the extreme value theorem to it to say that it must obtain its minimum and maximum. Now, because we know that at least somewhere the function goes above this value, we know that the function is not at its maximum at A or B. It's some other point inside the open interval AB where the function obtains its maximum. So I've called that maximum value that the function obtains capital M, and I've called the point within the domain where it obtains that maximum the point C. And as I have already said, we know that C is not A and it's not B. So my claim is that this point C, where the function obtains this maximum value, big M, is the C that is going to satisfy Rolle's theorem. It's the C where the derivative of the function is guaranteed to be 0. So how can I prove that? Well, because we know that the function is differentiable everywhere on the open interval AB, and we know that C is in that open interval AB, i.e. it's properly in between A and B, then we know the derivative is guaranteed to exist at C. So let's think about what it's equal to. Of course, here's its definition. It's the limit as h approaches 0 of f of c plus h minus f of c over h. Now, f of c is this maximum value, big M. So f of c plus h, whatever your h is, this value is going to be less than or equal to capital M. It could be equal to it, because of course there might be multiple points on the domain that obtain this same maximum value for the function. It's not guaranteed that there's only one point that obtains this maximum. You can imagine having a function that goes up and up and up like this and goes up to the same height each time. Then it would have multiple points that all obtain that same maximum value. So it is possible that f at c plus h is equal to m, but what we can say is that it's guaranteed to be less than or equal to m. So then if you look at what that minus that is equal to, what delta f is equal to, it's always going to be less than or equal to 0. And that's the case for positive h's where you're going forward, and you can see on the picture, in this case, if you go forward, the value of the function is going down, so f of c plus h is guaranteed to be less than f of c, so this is going to be negative. And if you go backwards, again the function is going down, so f of c plus h, so this is negative h is going to be less than f of c, so again this numerator is going to be negative. But in general, we can't quite conclude that it's less than, strictly less than 0, but we can conclude that it's going to be less than or equal to 0. So to help us understand why we can now conclude that this limit is going to have to equal 0, I've plotted the gradient of these secant lines, i.e. this quotient, this rise over run quotient here, as a function of h, as a function of how much we're changing the domain by. So this rise over run quotient is going to be defined between values a minus c, that's the smallest it can go to, and that will take you right back to a, and then b minus c, which is the most you can go forward, which will take you right up to b. And it's going to be defined for all points on this interval except for the point h is equal to 0. Now, for the case that h is a positive number, so it's greater than 0, you can conclude that the value of this rise over run quotient, the gradient of the secant lines, is always going to be less than or equal to 0. So it's going to be non-positive down here on the graph. And the reason you can do that is we know that delta f is always going to be non-positive, less than or equal to 0. Then this thing that we're dividing through by is now a positive number, so that means that overall you're going to end up with a number that cannot be positive. So if it's a negative number, delta f, then you're dividing through by a positive number, you'll get another negative number. If it's equal to 0, you're dividing through by a positive number, you'll still end up with 0. So on this side of the graph, where h is greater than 0, you can always conclude that the value of this rise over run quotient, the gradient of the secant line, is less than or equal to 0. And that corresponds to our picture here. If you draw one of these secant lines from this point C forward to any of these points, and I've drawn this one on here, you can see that its gradient is always going to be a negative value, always less than or equal to 0 in general. Now the opposite case is if you go backwards, make h less than 0, go backwards and draw a secant line. You can see on our picture, if I go backwards to this point, for instance, and draw a secant line, that secant line is going to have positive gradient. And indeed, if I go to any of these points, in fact, and connect it up to my point CM, I'm going to get a positive gradient secant line. So looking at this in more generality without the picture, we know delta f is less than or equal to 0, and we're now dividing through by a negative number. So if delta f is a negative number and you divide through by another negative number, you'll end up with a positive number. If delta f is 0 and you divide through by a negative number, you'll end up with 0. So you can always conclude that on this side of the graph, it's going to be greater than or equal to 0. So I've plotted what this function might look like for the function shown in our picture here. So I know that the function must be differentiable at c, because it's differentiable everywhere on the open interval ab. So this limit must exist, and it is either going to be greater than 0, equal to 0, or less than 0 by trichotomy. Now, I know that it cannot be greater than 0 and it cannot be less than 0, and that's how I'm going to conclude that it's equal to 0. How do I know that? Well, consider the case where it is greater than 0. If the limit exists, both the right-hand limit and the left-hand limit of the function have to exist, and they have to equal this value L. If it was greater than 0, then it is not possible that the right-hand limit can be equal to that limit L, because all of the values of the function to the right of 0 are less than or equal to 0. They are non-positive, so they're down here. How can they possibly get and stay indefinitely close, therefore, to a positive number? You know, the biggest they can possibly get is 0, and therefore the smallest distance they can be to this limit L is distance L, the modulus of L. That's the distance between L and 0. So that's as close as they can possibly get, so they can't get indefinitely close to this positive number L from the right. So that means its limit cannot be greater than 0, so we can cross that one off. And similarly, for less than 0, that's this one shown here, the left-hand limit cannot possibly equal something that is less than 0, because on this side, the function is always greater than or equal to 0, so again, it cannot get indefinitely close to that. Never mind get and stay indefinitely close to that. It can't even get indefinitely close to that, because the closest it can get is going to be modulus of this number L, so it's a negative number, so take its modulus, and that's the distance between it and 0. That's the closest it can possibly get from the left. So the left-hand limit cannot possibly equal a negative number. So therefore I can cross these two out. The only possibility then is that this limit is equal to 0. So therefore I can conclude that at this point C, where the function obtains its maximum, the derivative of the function has to exist and it's going to equal 0. Therefore this is the C that satisfies Rolle's theorem. So I've proven therefore that functions that satisfy this case are going to satisfy Rolle's theorem. So for functions in this final third case, as I said earlier, I'm not going to go into the details here, but I will quickly outline this for you. So we know somewhere on the domain there must be a value that is less than the value of the function at A and the value of the function at B. So I've drawn a picture here of a function that would fit into this third case and wouldn't fit into either of the previous cases, because at nowhere does it go up. So it doesn't fit into this case, and clearly it's not the constant function, so it's not this case. So if there is somewhere on the domain that is less than this value, then you can conclude by the extreme value theorem that somewhere the function must obtain its minimum because of the fact that it's continuous everywhere on the interval AB. And that minimum, importantly, you know that it's not at the point A or the point B, because there was some value in the domain that was mapped onto something less than that. So there is some point C in the open interval AB, i.e. in between A and B, that is mapped onto the minimum here. So we can call that minimum value little m. And it's this point C that is mapped onto that minimum value that is going to satisfy our C for Rolle's theorem. It is going to have derivative equal to 0 at that point, and you can see that from the picture here. So we know that the function is going to be differentiable at C because it's differentiable anywhere on the open interval AB. And you can conclude that the derivative is going to have to equal 0 at C by a similar argument to what we've used here. So if h is negative, that means go backwards and look at one of these secant lines, it's always guaranteed that the gradient of that secant line is going to be less than or equal to 0 in this case. So it switches sides, these inequalities in this case. Whereas if h is positive, then you're going forward and you can see that the gradient of those secant lines is always guaranteed to be greater than or equal to 0. So you can then apply the same logic as we used here. The right hand and left hand limits have to equal one another. There's these three possibilities and these two go away, so it has to be the case that it's equal to 0. So this is then your C that satisfies Rolle's theorem. So if a function obeys this criterion, we can conclude that it will have a point that satisfies Rolle's theorem. So now what we have done is any function that satisfies these criteria for Rolle's theorem is either going to be this function or it's going to satisfy at least one of these two criteria. And the moment it satisfies at least one of these criteria, you can conclude that there must be some point C properly inside the domain, so inside the open interval AB, where the derivative is going to equal 0. So that ends the proof, and we'll end the video there.